Today's guest is Dr. Jack Burns, a professor in the Department of Astrophysical and Planetary Sciences, and also professor at the Department of Physics, both at the University of Colorado Boulder. He also holds many other key positions at the university. Jack was recently the primary investigator for NESS, the Network for Exploration in Space Sciences. He also has long-standing ties with NASA and has served on their advisory council from 2008 to 2010. His research focuses on extragalactic astronomy and cosmology, observations of active galaxies and galaxy clusters using radio interferometers, optical telescopes, and X-ray satellites, supercomputer numerical simulations in astrophysical jets, and large-scale structures in the universe, and the design of low-frequency radio telescopes on the moon. He's also participating and is the lead investigator in the Farside program, which is something that we're going to be getting into today as well. So without further ado, my guest, Dr. Jack Burns. Dr. Burns, if you wouldn't mind just getting started here, could you tell us a little bit about yourself? And I'd also be curious to learn about, were you interested in these topics as a child, or was this something that you found later in life?
Yeah, thanks, James. It's good to be with you today. I'm an astronomer for almost 50 years now, going back to time growing up in New England and going to undergraduate school at the University of Massachusetts in Amherst. I do have a long-standing interest in the moon because I can think back to my first science fair project that I did in the 8th grade, and it had to do with the Apollo program. How Men Will Reach the Moon was the title of the science fair project, and we won first prize. I built some models of the Apollo mission. So who would have thought then back 55 plus years ago that we would be working today to see the first landings of radio telescopes on the moon that I helped to design and to operate. More recently, I've been introduced to the potential for doing radio astronomy on the moon. By more recently, I mean now 40 years ago, that a colleague asked if I had ever thought about putting a radio telescope on the moon. This was 1984. And I said, no, I hadn't really thought about that much. And so he asked me to do so. He was at NASA Johnson Space Center and asked me if I would come to a conference he was putting together at the Johnson Space Center and present. And that was my first paper that I had ever written on radio telescopes on the moon. Who would have thought it would be 40 years until we actually did get that first telescope on the moon, which happened just recently in February as part of NASA's new commercial lunar payload services program. We were able to carry a radio telescope called Rolls's to the surface.
And is that part of the Farside initiative?
No, Farside is an experiment that's going to come later. This first mission and the first few missions that we will do as part of this CLIPS program are just single telescopes. And Farside is an array of low frequency radio telescopes, hundreds of telescopes that will be electronically phased together and will be located on the far side of the moon.
Okay, I see. So that's sort of the future program. The plan ultimately is the Farside.
That's right.
I actually have, right on. I have a fascination with the moon as well. In fact, on my radio show, every week we do a report about the moon. So we talk about the status of the moon and which phase is it in and when can you best see it. So we're not getting quite nearly as deep as you have, but I'm trying to share that with other people as well. Since we touched on Farside, and that's something that I was kind of reading up on in preparation for our discussion today, I was hoping you could just go into a little bit about Farside, and then I have some other particular questions that I've been interested in that we can dive into too.
Yeah, so Farside is actually an acronym for an array of low frequency radio telescopes to observe the very early universe's dark ages, as well as to do radio observations of exoplanets to investigate whether or not they have magnetic fields. So this array of low frequency telescopes, we have somewhat similar arrays of telescopes, but operating at higher frequencies already on the Earth. We've been doing radio astronomy with what are called interferometers now for 60, 70 years, very successfully. But we can't go down to these interesting low frequencies that are below the FM band because for a variety of reasons, one being that the ionosphere cuts off at low radio frequencies below 20 or 30 megahertz. And secondly, the Earth is also polluted with a lot of low frequency human-made radio interference from transmitters and antennas all over the globe. So in order to open up this last wavelength window to the electromagnetic spectrum at low radio frequencies, you have to go into space, and particularly to the far side of the moon where it's radio quiet. The far side of the moon is unique in that the moon is what we astronomers call tidally locked. So one side always faces towards the Earth. That's the man in the moon face that we're all used to looking at. And the other side is always facing away. So when you're on the far side, you're always on the other side away from the Earth. And you've got 2,000 miles of rock, which is blocking any radio emissions from coming. So that's where we want to locate this array of about 256 radio telescopes that will be spread over a diameter of about 10 kilometers.
Right on. And you mentioned particularly the low frequencies being the goal. Why exactly are low frequencies of interest?
Yeah, because they are areas that we can uniquely probe some new and achieve new information about aspects of the universe. So, for example, I mentioned earlier exoplanets. So, what is it about exoplanets that we can do in low frequency radio? Well, it turns out that every planet in our solar system with a magnetic field, including the Earth, emits low radio frequencies. And it comes from the fact that high energy electrons emanating from the sun get trapped in the magnetic fields of the Earth and the other planets, spiral in there and generate emissions generally below a megahertz, so well below what we can see from the Earth. In the case of the Earth, this is called the auroral kilometric radiation and was first observed in the early 1970s with several NASA space probes. And the reason that's interesting is because that low frequency radio emission tells us that these planets have magnetic fields and actually allows us to measure what the magnitude of magnetic fields are. Magnetic fields are important for the Earth because they help shield us from the solar wind, and that really has allowed life to exist. So contrast that to Mars, for example, which its magnetic field shut down 2+ billion years ago. And so you can see that today now Mars is stripped of most of its atmosphere. The solar wind has blown it away. There's no water currently on the surface, and it's pretty much a dusty desert planet at this stage that really no obvious life forms are there. Contrast that to the Earth. So let's fast forward and go to the exoplanets. So we know that there are dozens to hundreds even of exoplanets that have been detected in our solar neighborhood, going out to 30 or 40 or 50 light years away from the Earth. And we'd like to know which one of those might have life. So one of the criteria is how close is that planet away from the star? Is it in the area where water the temperature is such that water could exist, because that's important for life. Okay, that's number one. But really, number two is, does it have a magnetic field around it to potentially safeguard that life as it's forming? And so it's only using these low radio frequencies that we could detect that magnetic field. So going to the moon, going to the far side of the moon with a sensitive array, we can, for the first time, observe the known exoplanets and determine which one of these has that low frequency radio emission. Does it have a magnetic field? And even what is the strength of the magnetic field? So we could calculate whether it's strong enough to protect any life. So exploring habitable worlds, as they're called, is something that's going to be very exciting in the next few decades.
Yeah, I'm
So
fascinated by that. And
that's one example, James, of the kind of new science you can do.
okay, I'm curious. So you mentioned the exoplanets. Obviously, presumably, a lot of those exoplanets would also have moons that orbit them. Would there be any focus on those moons, or are we primarily interested in the magnetosphere for these planets because of that protection? I guess I'm curious about the possibility of um, something that's perhaps not carbon based being life form. I'm just curious if you guys have any thoughts around how do you approach the moons and things like that.
Yeah, well, I mean, some of these planets are likely to have moons because we know moons are very common, even in our own solar system. We look at Jupiter, Saturn, Mars, Uranus, Neptune. They all have many, many, many moons, and even asteroids have moons around them. So that's a common feature. So it's likely exoplanets are going to have moons as well. And sometimes those moons are interesting because in the case of Jupiter, the moon Io has a magnetic coupling between its surface and Jupiter, and that produces what's called a magnetic torus that moderates the radio emission, which is coming from Jupiter. We've known that for some time. Could there be similar connections like that with other planets around other stars? There are suggestions in a few cases that exoplanets may have moons associated with them. So it's a very interesting topic, and one that again will surely be explored further with optical infrared telescopes, as well as beginning to introduce radio telescopes into the mix.
Okay, I see. Yeah, the reason I bring that up is because I was reading an article and I'm forgetting the lady's name, but she's been researching the atmosphere of a particular moon, I believe around Jupiter, and noticing that there was phosphorus, or at least indications of potential phosphorus in that atmosphere. And from what I understand is that we don't know of phosphorus being produced from non-life processes. So that was something of interest. I guess in that case, in order to detect that phosphorus, you would be using something other than radio in that
Yes,
case. And so radio would be geared
using more
towards,
standard spectroscopy in the
okay,
visible and infrared parts of the spectrum.
right.
But
I
we
see that makes sense.
astronomers like to use all of the tools that we have available to us. So the James Webb
Right.
Space Telescope, the Hubble Space Telescope, our far side radio array on the moon, which we hope to build in a few years. So all of them will come into play to help us understand, exoplanets, planets in our own solar system, and then, as I mentioned before, also the dark ages of the early universe.
Very cool. I want to ask you something about James Webb, but before I do, just to kind of close the loop on Farside, I'm really interested in what are the potential challenges about putting something on the far side of the moon as opposed to the near side of the moon? Are there important concerns that we need to consider when we're working on that aspect of the sphere?
Yeah, in the case of the far side, you need a communication satellite to be able to relay the data back to the Earth because, as I said, the far side blocks all of the radio emissions, including communications to the Earth. So we have a mission called Lucy Night, which is scheduled to fly in 2026. And it will go to the far side of the moon. And in the process, this NASA mission is going to bring with it also a communications satellite funded by the European Space Agency. We'll put that in orbit of the moon. We will land our lander, and that communication satellite then will relay the data back to the Earth. So that's certainly one of the considerations. Otherwise, the near side of the moon and the far side of the moon are very similar. They receive equal amounts of daylight. So it's about 2 weeks of daylight and about 2 weeks of darkness.
Okay. Out of curiosity, I understand that there is a lot of value in being able to have a north-south orbiting satellite for the Earth because you get certain aspects of viewing parts of the Earth as opposed to orbiting, I guess more or less we'll say left to right. Would we have any of the same benefits in this scenario for orbiting vertically on the moon as opposed to horizontally? And in which case are we going to be using this satellite?
Yeah, well, that, for example, the Lunar Reconnaissance Orbiter, which has been in orbit of the moon now for well over a decade, has a north-south orbit, and it precesses with time. So it's able to sweep over all parts of the moon, and its primary goal is to do imaging of the surface of the moon and to understand the topography. So that's a good example, and a number of future communication satellites where we're going to be emphasizing, in terms of exploration of the moon, the two poles, particularly the South Pole, where we think there's water ice on the moon, and so having satellites that go over that polar region is going to be important.
I see. I didn't know that there was the water ice. That's fascinating. Okay.
It is. That's
Um,
one of the discoveries that was
yeah,
made after Apollo, and first uncovered by a couple of satellites 10, 15 years ago, including one from India that indicates that the moon is not nearly as dry as we thought. There are some permanently shadowed craters near the poles that just, the way the sun angle is, that they just never really get any sunlight. So they've been very cold for millions of years, and water molecules tend to collect in what are called cold traps in these regions of permanently shadowed craters. So we believe there's a substantial amount of frozen water ice there that is going to be valuable for future exploration.
okay. So when you mentioned the water, I was thinking that it would have come from perhaps something else in space that, like just a frozen block of ice, we'll say, right? That hits the moon. But what you're saying is that it's almost condensing like a morning dew in a way.
Yeah, it's actually coming from a number of sources. Certainly, comets, which we know have an abundance of ice and may have contributed to produce the oceans on the Earth, have been hitting the moon for billions of years, and so some of that water ice collects. But even the sun has hydrogen and oxygen in its solar wind, and that impacts on the moon, and those atoms combine into water molecules as well. So you've got a multitude of processes. And even going way back to the formation stage of the moon, 4.5 billion years ago, volcanic venting, which probably occurred in abundance on the moon, the outgassing had a lot of hydrogen and oxygen and water that some of which may have been preserved in the moon, in the interior of the moon, and then these coal traps.
Okay, right on. I wasn't going to ask you this, but now that we are talking more about it, so is there a consensus on where the moon ultimately came from? Because I've heard a couple of different theories about its origins, and I was just curious, just kind of popped into my head. Could you speak to that a little bit?
Yeah, I think the consensus in the lunar community these days is that the moon is the result of a collision between a Mars-sized asteroid, not Mars itself, but a Mars-sized asteroid, very early on in the formation of the solar system, where we knew there was a lot of collisions and bombardments. And that object struck the Earth, It penetrated fairly deeply. And so a lot of that proto-Earth, almost into the core, then was combined to produce both the Earth that we have today, as well as the moon, which is a combination of Earth material as well as that asteroid. And
I see.
we see that from, for example, the Apollo astronauts, the samples that they brought back have that kind of composition. So the Apollo program pretty much sealed the deal in terms of that model, that collision model for the formation of the Earth-Moon system.
Gotcha. Yeah, I had heard somewhere that there was an idea that maybe something was basically kind of flying through space and ended up getting caught in the gravity of the Earth, but it just never seemed like that made whole bunch of sense, I suppose.
Well,
What
in
you're
some
describing
sense,
is
that is the model that we're talking about because early on
right,
the
but
solar
there
system
was an
was
impact
littered with
ultimately.
these, yeah, it was
Yeah,
littered with these giant asteroids, and a lot of those are combined together now. Some have fallen into the sun. A lot of it is combined within the planets, and so the solar system is pretty well cleared out now compared to what it once was. It was a lot of collision, very violent early history of our solar system. A lot of collisions, a lot of banging of objects into each other and creating new bodies.
I see. Thank you for clarifying that for me. I was curious if you could speak to a little bit about the impacts of commercialization in space. So, in the articles that I was reading in preparation for this, it talks a lot about how, in the past, NASA was the primary and the only organization, at least in the States, that was actually doing the process of building, designing, and actually launching various things into space. Of course, now we have all sorts of companies that are doing this. Could you just maybe give us a little bit about your perspective on how that's changed space exploration?
Yeah, and it's changed dramatically over the last 50, 60 years because you're absolutely right. Russia and the old Soviet Union and the United States were the two dominant space powers in the 60s and early 70s. And they're the only ones and we specifically, the United States, were the only ones that could put the kind of dollars that were necessary to do an Apollo program. At one point, NASA's budget was almost 5% of the total GDP of the United States. Today, it's 0.4%. So it's a factor more than 10 less than what it was during Apollo. I would love to have that budget during the Apollo era. Imagine what we could do with it. But it just shows you over the 50 years, 1972 was the last human landing on the moon with Apollo 17, the technology has advanced substantially so that now individual countries and individual companies, like the Intuitive Machines company that brought our radio telescope to the moon just a month or so ago, can build their own lander, fly it, using private launch companies like SpaceX to get to the moon. That's a remarkable transition. And it leads us, as I like to tell my students all the time, into what I think will be an era of sustainability in space. Because Apollo was never sustainable. It was too expensive. The technology really wasn't there to develop a permanent presence on the moon. All of that has changed today. So you've got dozens of companies and at least a half a dozen countries who have active lunar programs. And they're going to be over the next decade or more, beginning to have a permanent presence on the moon. We'll see some mining, we'll see some manufacturing, we'll see companies that will have business plans to take that water ice, turn it into rocket fuel, and sell it back to individual uh, space agencies, for example, or companies to do further exploration of the solar system. So it's a very exciting, very entrepreneurial new environment in space that reminds me very much of the personal computer revolution that took place in the late 70s and the early 80s.
Sort of a democratization of space in a way, which is really exciting.
And the same with
I'm curious.
that
Yeah,
took place with computing, because
right,
before that you had to you only a few people had access to large mainframe computers, whereas today everybody has it.
right. And that's changed everything at the end of the day. So you mentioned that it's been since 1972 since mission to Mars, or excuse me, a mission to the moon, Apollo, and that was a manned mission. But why do you think it's been so long since we've done something like that? Why has it been 54 years?
Well, it's just for the reasons I said a few moments ago. It's expensive,
Yeah,
and the technology really wasn't there to allow sustainability. There wasn't a good business model, to get private industry involved. So I think all of that's changed. And the moon is just the logical stepping stone into space. It's so close. It takes 3 to 5 days to get to the moon. Mars, it takes 8 months to travel there. So it's a very long distance away. So the moon is just a good place to learn how to live and work on an alien airless body that will give us the practice for what we need for further exploration. So it's really, it's taken time for the technology to catch up and for the costs to go down.
right. And I can see maybe in the future we'll do a lot of industrial work out in the moon, on the moon and in space, building
Yes,
of
yes.
factories and things
Yeah, I
like
mean,
that.
there's some people with visions. I mean, Jeff Bezos talks about putting 1 million people on the surface of the moon to live there sometime in the, in this next century or later this century. That's
Incredible.
certainly a very ambitious vision. Whether or not that will actually happen, we'll have to see.
Right. Well, shoot for the moon or shoot for the stars, land on the moon, I suppose. So, Jack, I want to respect your time and we're just wrapping up here. I really do appreciate you hanging out with me for a bit. One thing that I was curious about, something that I've been reading into is kind of related to your work as a consultant at the Space Plasma Physics Lab at Los Alamos. And I've been reading about the idea or the conjecture that perhaps plasmas, not all plasmas, but some plasmas, may actually be a form of essentially non-carbon based life. And I was just wondering if that was something that you had ever heard or were familiar with, and if you could speak to that a little bit.
Well, I think there's just in general a lot that we don't understand about life, because we only have one example here on the Earth, a carbon-based life form. It makes sense for our planet. And water makes sense for being the basis of how life forms, but maybe on other bodies like Titan, for example, where you have liquid methane, which is on the surface, might we have just a very different kind of biology? We simply don't know because, with one example, it's very difficult. So I think there's a lot of work to be done in the future, and a lot of discoveries and probably surprises that come from looking at life and maybe visiting other parts of the solar system. Mars, Europa, Titan will give us some eventual insights and maybe some other examples.
I see. Really cool. Thank you for that. So just to wrap it up, I'd love if you could just give people some information about where they could find more about you and your work. And if people are interested, I understand you have a university email if they want to contact you through that. I presume that would be the best contact method if they're interested.
Yeah, and folks can just go to my website. You can just Google me at Jack Burns at the University of Colorado, and you can find my email address and my web pages for various different missions that we have. That's probably the best way to start.
I see. Well, thank you, Dr. Burns. I will go ahead and stop this recording now. It's been a real pleasure and an honor to spend some time with you today.
It's been a pleasure, James. I've enjoyed it.